Reactor B.
0C. Trinary 0C solar collector.
Nice.
Yeah.
I like it, man.
There's the fusion reactor. So the dome has to be in the middle. The trinary comes from PV, which is electrons flowing.
Mm-hmm.
Let's get one little electron flowing out of there.
Nice.
An electron. So that's the first of the trinary. The second one is our liquid. So we've done that in black. Two ways to do it. One is a counterflow, where you've got your liquid coming up with turns at least 2 degrees of slope. Less is not enough. More is wasted space. Or you've got parallel flow here with your liquid in black, which is the second leg. We do have a commercially available panel.
From
Static Cool PV is the liquid.
Nice.
And then the blue is air. And so the air is going to be sort of a faster time constant for living space. So they're going to be, if you want it cooler, you'll pull from your cool side of your thermal battery. If you want it warmer, you pull from the warm side of your thermal battery. So again, trinary electricity. There's your E- for electrons. Second portion is your black for your liquid. And then the third part is your blue, which is your air. And then for seasonal storage, what we've got here is January 1, June 30, December 31. This is sort of your sinusoid of nature. Cold in the winter, warm in the summer, again cold in the winter. But your demand is the exact opposite. You need it warmer in the winter, cool in the summer, and again warmer in the winter. So the thermal battery, which a portion of it sits on the roof up high where you're closer to the fusion reactor. Another portion sits underground, and of course it has to be insulated as well, so you can achieve this smooth flow.
Nice.
And then of course it's all zero carbon, no fire.
Sweet.
Yeah.
Hey, Brad, here we go, man.
All right. So we're looking at the tethered kite turbine. This is going to be one of the projects we do in the 2017 practicum up in Browning. This is going to be based on the lighter than air wind turbine that we did here in Missoula in 2012, where we floated a SAVONIUS turbine from our hydrogen balloon. So diving in here a little bit. First thing we want.
Where's the SAVONIUS at?
Yeah, we've got SAVONIUS right here
Nice.
as propellers. In this particular design, this is the manta ray. So we're kind of looking into the mouth here, and what you can see would be turbines that are sitting. They're again SAVONIUS. So you've got catchment here. So if you could imagine two separate blades, one facing one way, one the other. As the wind hits it, it spins. So here's your catch side, and then you get this kind of rotation. And we thought, well, let people use reusable plastic bottles. This guy might be a little too flexible, a little too squishy. So the next idea was to take the entire bottle, put it in some warm water that we could do with solar thermal, and then compress it. That gives us a stiff top, stiff bottom. And now we've got the two bottles, one up, one down, and now we can get our rotation from that. So we still need to build a platform. Once we've got our mechanical design finished, then we attach that to our generator. So this is actually the generator that came out of the 2012 turbine. There's a pair of magnets in there. The rotation from the SAVONIUS turbine up top spins that guy. We send that through some 28 gauge wire. So the spinning magnetic field creates an electric field, and these are the 28 gauge wires that we can send electricity back down. So this is our first little prototype on that. So taking that to full scale, what we'd really like to do, rather than using the hydrogen, so the hydrogen station's in storage right now, we're going to use a kite. So we're either going to use John Pickens' Eagle Kite, or one of these larger kites that you see the windsurfers using, the wind boarders. So up here on the left, we can see a shot of a kite. And again, this would have, rather than a SAVONIUS action, it would have a Darius. So we got the wind coming in from this direction. We've got our lift vector, and we've got our drag vector. And so below that, we can see hanging a pair of turbines. So this is top secret information that we may have to engineer the directions these turbines spin in order to reduce the torque so the whole mechanism doesn't spin. Because again, the turbine itself has to remain stationary. We've also decided we're going to need a mechanical control, human in the loop, once we get up there to Browning, because the wind's going to be quite strong and could be variable. So in order to control it, what we thought we'd look at is a 4-tether system, so we can control both pitch and rotation. So we can change the angle of attack, which is our pitch, and then we can also change not our yaw but our roll. So we don't want it to roll out of control. So with 4 chords, we can control both pitch and roll with a single human in the loop. We didn't draw him down here, but we're thinking if we get one guy who's actually tethered himself to the ground, then we've got the human in the loop. So you can imagine somebody. We've got the jumpsuit. Let me grab the jumpsuit here. You don the jumpsuit. You lock in here. You can imagine the control arms coming out of the suit itself, and then in the rear, of course, you've got the guy tethered to the ground. So, looking for volunteers.
Yeah. Some of those big backseat guys, man.
Man, so get Austin Heavy Runner in there.
Hey, Austin Heavy Runner.
Dialing that in. So, that's the basic system. We'll also run through some mass. We've written Bernoulli's equation to show lift and drag on how this guy takes flight. And then ultimately what we'd like to do is send the electricity back down with at least 12 volts, charge a cell phone, charge a battery, and get some zero carbon electricity out of this system. So looking forward to 2017 practicum in Browning.
Yeah, man.
All right, we'll see you all there.
Nice job, Dr. Layton.
All right, thanks, Jay Bowe.
You rock, man.
We'll be there.